Video we are going to focus on question 2.1. Now we are given a binomial experiment consisting of n trials, and it resulted in the observations of y1, y2 up until yn, where the is going to be equals to 1 if the ith trial was a success, and it's going to be 0 otherwise. So it's going to be 0 if it was a failure. Now we let y equals to the sum from 1 to n of our individual yi's. Now if the maximum likelihood estimator was found to be p hat equals y divided by n, recall that our y is equals to the sum from 1 to n of our individual yi's. Now if we have the MLE being equals to y divided by n, now if p hat is equals to y divided by n, and recall that our y is the sum from I equals to 1 till n of our yi's, now divided by n, this is the same as our y bar, the sample mean. Excuse me. Now we need to determine whether the MLE is asymptotically efficient or not. Now for asymptotic efficiency, we need to inspect the Kramer lower bound, which is the variance of our maximum likelihood estimator, and we compare it with the asymptotic variance. If our variance of if the variance of the MLE is greater than the asymptotic variance, then our maximum likelihood estimator is efficient. But if it is equals to, if the variance of the MLE is equals to the asymptotic variance, then it is asymptotically efficient, and it's the minimum variance unbiased estimate. Now we are firstly going to inspect the variance of our estimator. Recall that this is a binomial experiment, so we have a binomial distribution. So the PDF of the not the PDF, the probability mass function, the PMF of a binomial distribution is given as n choose y, and then we have p raised to the exponent of y, and then we have 1 minus p raised into the exponent of y, n minus y. Okay, and the mean of a binomial distribution is np. The variance is actually np into 1 minus p. Okay, so now we are going to inspect the variance of our MLE, which is this one right here. So now the variance of our p hat, which is our MLE, it's going to be the variance of our sum of yi's divided by n. Now we are going to take out the constant, which is 1 divided by n, and we square it. Sum of your yi's, I equals 1 till n. Now we are going to take out the sum of yi's, the sum, not the sum of yi's, the sum. Now to get rid of this I, individual i's, we are going to multiply it by n. Now this will be the variance of y divided by n. Recall that the variance of the binomial distribution is this. Now this will be, so the variance of our maximum likelihood estimator is going to be np into 1 minus p divided by n. This will cancel with that. Actually our variance will be p into 1 minus p. This is the variance of the MLE. Now we need to find the asymptotic variance uh, for us to inspect the Kramer lower bound. This. Now we need the asymptotic variance. For us to find the asymptotic variance, we are gonna use a similar approach when we are trying to find the maximum likelihood estimator, but instead of taking the whole sample of our yi's till n, we are just gonna take one individual y. So by that I mean we're gonna take one y, which is n choose y, p raised to exponent of y into 1 minus p raised to the exponent of n minus y. This is the probability mass function of the binomial distribution. So we are gonna take the logarithmic function of this, the logarithm of this, which will be the ln of n choose y. Not sure about the ln of this, but it's not quite important. So it's gonna be the ln of this will be y ln p, and then plus n minus y ln 1 minus p. Okay, now we are gonna take the derivative of this logarithmic function in terms of p. Now the derivative of these parts, which is why I said it's not going to be important, it's just going to be 0 because we are deriving with respect to p. And then the derivative of this will be y divided by p, and the derivative of this part is just going to be plus n minus y divided by 1 minus p, and then we multiply by the derivative of the inside chain rule, which is going to be negative 1. If we multiply this by negative 1, we're just going to have no. We're going to have minus here. And then after this, we are going to take the second derivative of this logarithmic function of our PMF. Now this will be, take the second derivative with respect to p. Now this will be negative y divided by p. P squared minus n minus y divided by 1 minus p all squared, because this is just going to be minus, and then we multiply by the derivative of the inside, which is going to be, no, it's not going to be the derivative of the inside, because the derivative of this is more like negative n minus y into 1 minus p raised into exponent of 1. So if you multiply this, it's going to be plus. So we're not going to use the derivative of the inside. Now we carry on. We need to find this asymptotic variance. So for us to do that, we are going to start with this. First things first. Now it's going to be, did I use theta there? It has to be p, not theta. Now to find this, we are going to have negative e, negative expected value of the second derivative of our logarithmic function of our PMF with respect to p. Now this will be expected value of negative y divided by p squared plus ny n minus y divided by 1 minus p squared. Okay, now we are gonna distribute the expected value and leave the negative side outside, so it's gonna be negative expected value of y divided by p squared plus expected value of n minus y divided by 1 minus p all squared. Now this will be negative into negative expected value of y divided by p squared plus e expected value of n minus y divided by 1 minus p all squared. Now we're gonna distribute this expected value on the inside. Now this will be negative expected value of y divided by p squared plus n minus expected value of y divided by 1 minus p all squared. Now recall that the expected value of y, or the mean of our binomial distribution, is just np divided by p squared. This is going to cancel with that. Now it's going to be n minus np divided by 1 minus p all squared. Now in here we have a common factor, which is n. Now this will be negative n divided by p into n, take out the common factor 1 minus p divided by 1 minus p all squared. Now we are gonna have negative into negative p n divided by p, and then n divided by 1 minus p. Now we take a common denominator, which is gonna be negative into p and then 1 minus p. Now we are gonna multiply the n with 1 minus p, n into 1 minus p, and then minus, we are gonna multiply the n with a p, np. Now this will be negative into negative, so negative and negative will cancel each other. P into 1 minus p, we'll have n minus np minus np. No, I think there's a mistake I made here. I'm still looking for the mistake I made. This was plus all along. This was plus. I don't know how I did this mistake. So this was supposed to be plus. So we are adding here. So we were not supposed to subtract. So this will be positive. That's the mistake I just made. Nothing changed. We just made a mistake with the signs here. Now this is gonna cancel out with this. Negative and negative are gonna cancel out each other. Now we'll have n divided by p into 1 minus p. This is our I. And we are going to multiply this with n. It's going to be n squared divided by p into 1 minus p. And then we're going to take the reciprocal of this. One divided by n, 1 p into 1 minus p. Now this will be just p. This was squared, so it's n squared, p divided by p into 1 minus p divided by n squared. Now our asymptotic variance is this, and recall that the variance of our maximum likelihood estimator, it's this. Now we are going to check the Kramer lower bound, so p into 1 minus p. Now p into 1 minus p, if we check this, if we compare this, the variance of our MLE is quite greater than the asymptotic variance, then we can conclude that p hat equals to y divided by n, and recall that y is equals to the sum of your yi's, I equals 1 till n. This maximum likelihood estimator is efficient for our parameter p. But the question was asking if it was asymptotically efficient. We are saying it is efficient because the variance of our MLE is just greater than the asymptotic variance. Then we can say it's efficient. If the variance of our MLE was equals to the asymptotic variance, then we would conclude that it is asymptotically efficient.